I'd like to talk today about using a novel ex vivo placental perfusion chamber to validate in vivo magnetic resonance fingerprinting. I have no financial interests to declare. The placenta is the site of exchange between the mother and fetus, and using MRI to evaluate oxygen transport has been proposed as a more specific, non-invasive tool to monitor placental function in cases of fetal growth restriction or preeclampsia. Relaxometry, that is, estimating MRI relaxation times, such as T1, T2, or T2 star, is one way to assess placental oxygenation and also gives information about tissue microstructure. We have been working on applying advanced relaxometry approaches to the placenta, but this is challenging since the placenta moves and is deformable. MRF stood out to us as an initial approach to try because it is fast and yields intrinsically co-registered parameter maps for T1 and T2. As a very brief summary of how MRF works, in under 10 seconds we acquire a series of undersampled images like this one, and then examine the signal evolution on a voxel-wise basis. We look up the observed signal evolution in a dictionary of simulated signal evolutions for different tissue parameter sets, and select the signal that best represents the observation to estimate the underlying parameters. MRF is still undergoing rapid development, and new approaches are typically validated on phantoms. The NIST ISMRM Relaxometry reference phantom allowed us to validate our MRF implementation and approach for slice profile correction. Our 22-week fetal phantom with realistic anatomical features in compartments containing doped water or agar to reflect the expected tissue properties allowed us to validate our approach to B1 plus field inhomogeneities. However, insanity check experiments comparing our in vivo MRF T1 and T2 estimates with inversion recovery haste or spin echo EPI estimates of the same, we continued to see discrepancies. So we began to wonder if there was some aspect of the placenta we were not capturing in our phantom validations. We knew the placenta is over 50% blood by volume, which contrasts dramatically with the adult brain, which was the initial target for MRF development. Flowing blood pool is not accounted for in the MRF dictionary simulations. We did not find information in the literature about how a moving blood pool might affect the MRF measurement. In cardiac imaging, there was noted agreement between ventricular blood pool T1 and T2 estimated by MRF and reference methods, but this was not systematically investigated. So we took advantage of parallel work in our group that developed an ex vivo placental perfusion chamber that was MRI compatible. Instead of investigating placental biology using the chamber, we thought to use it as a biological phantom to mimic the physiological flow in the placenta in a controlled environment, without motion, and where we could modulate the flow to the fetal and maternal sides of the placenta as we desire. This platform enabled us to test the effects of flowing spins on our MRF-based placental relaxometry. On the left is a diagram of the perfusion system as set up in the MRI suite. Green represents the fetal perfusion system that is driven by a syringe pump mimicking pulsatile flow from the fetal heart. Perfusate, which is buffered saline, flows to the fetal side of the placenta through catheters inserted into the umbilical arteries. Purple represents the maternal perfusion system. It is driven by a peristaltic pump, and perfusate enters the intervillous space through 32 catheters inserted through the basal plate. Yellow represents the gadolinium contrast that is administered via a power injector, just like in human contrast-enhanced studies. To test the effect of flowing spins on MRF parameter estimates, we performed a series of MRF acquisitions as we modulated the flow state to the fetal and maternal sides of the placenta. On the right is an example timeline from one experiment. We took an initial pump-off measurement after setting up the system, and then turned the pump on and took measurements over the first 5 minutes. Then we alternated 1-minute periods of pump on and pump off, taking an MRF measurement 3 seconds after the pump state change and then 30 seconds after that. We did this for 3 cycles. In addition to MRF, we performed contrast-enhanced angiography to visualize the achieved ex vivo perfusion. We used multiple flip angle vibe to measure reference T1 and multiple echo time spin echo EPI to measure a reference T2. B1 plus mapping was used to correct the vibe and MRF parameter estimation. We scanned 4 placentas, 2 perfused only through the umbilical cord and 2 through both the umbilical cord and the intervillous space. All deliveries took place around 40 weeks. Here I show the sine coronal MIP of the 4 placentas when contrast was injected into the fetal circulation. I hope you can appreciate the more and less well-perfused placental regions. I drew perfused region masks that are used in the subsequent analysis, since I was interested in the effects of flow on MRF. These are example maps from both MRF and reference techniques for placenta 2. You can see how the buffered saline perfusate seems to cause T1 and T2 to be higher in areas of good perfusion on the right side of the placenta. And this makes sense based on the volume fraction of water in perfused versus unperfused voxels. Looking at the correlation plot between MRF and reference techniques for T1 and T2, we see that MRF is consistently underestimating both parameters. This is not a comparison to gold standard relaxometry techniques. In other words, the reference values may be biased as well. But assuming the reference techniques are accurate, MRF T1 is on average 200 milliseconds underestimated, and T2 is on average 50 milliseconds underestimated. I'm using this average bias to contextualize the magnitude of the flow effects on MRF that I will now show. Here for fetal flow, the dots are median values from the perfusion ROI defined with the aid of the contrast-enhanced imaging. I plot the MRI estimated parameter of interest versus time of acquisition. We began with a baseline no-flow pump-off measurement. This was followed by a period of pump-on. We then modulated the pump state between off and on in 1-minute intervals. This is the corresponding T1 data. This is the second placenta we scanned with very similar patterns to what we observed in the first placenta. For the initial pump-on period, we modeled the perfusate filling the placenta as one would a charging capacitor. The average time constant for T2 was 270 seconds and 126 seconds for T1. We interpreted this to mean that we should charge the placenta for at least 5 minutes to reach a steady state before doing quantitative imaging in this ex vivo placental perfusion chamber in the future. We then fit a linear mixed effects model to the cycles of changing pump state to see if we observed a significant effect of flow on parameter estimates. In blue, we see that flowing spins produce a significant underestimate in T2 of approximately 8 milliseconds, but not a significant difference in T1. This is consistent with our understanding that MRF is most sensitive to T1 in the first few seconds of the acquisition following the initial inversion pulse, but T2 sensitivity is built over the duration of the acquisition. Inflowing spins have more time to affect T2 estimates. On the next two placentas, we perfused the intervillous space, and here is the contrast-enhanced imaging showing the regions we successfully perfused. We were simultaneously perfusing the placenta through the umbilical artery during this time, and I showed that perfusion earlier. Admittedly, the perfusion is patchy. Individual lobules are well perfused, but others are not. We repeated the same analysis step of only examining MRF parameter estimates in the well-perfused regions. These are the results in the same format I showed previously. We allowed the placenta to reach equilibrium for 5 minutes before commencing the flow modulation experiment. We fit the same statistical model again and found a similar result, that flowing spins significantly affect T2 estimates, but not T1 estimates. These results come from modulating the maternal-side perfusion state whilst the fetal side is continuously perfused. We don't yet have data about whether these effects are additive. However, each effect accounts for 8 to 11 milliseconds of the overall bias of 50 milliseconds we observed comparing MRF and spin echo EPI. In conclusion, our ex vivo placental perfusion chamber was used as a biological perfusion phantom to investigate the flow sensitivity of MRF. Flow in the placenta leads to an underestimate in T2, and this has two implications. The bias may be regionally variable depending on perfusion rates, and the bias may be related to physiological state if flow changes during contractions with maternal position or during maternal oxygen breathing, for instance. Even accounting for the flow-related bias, there remains some discrepancy between MRF and reference methods, which requires further investigation. We expect that this platform will enable us to explore methods to mitigate this flow effect, as well as to investigate the flow sensitivity of other MRI sequences when applied to the placenta, for instance, arterial spin labeling or diffusion MRI. Thank you for your attention.